but in the powder form. And for that purpose, how do you know that the powder will react at that particular temperature? You do DTA of the sample or DC of the sample. The DTA or DC, for example, tell you about the glass transition temperature, about the startup crystallization temperature, about the peak crystallization temperature, about the melting temperature of the material. Once you have known these, then you want to make the phase, you want larger size crystal, calcine it here. If you want small size crystals, calcine it here, so that for the small size crystal you make the nearest neighbors to come together and larger grains do not form. So the aluminum, the magnesium and silicon and oxygen form small crystals inside the material. And if you need large size of the crystal or more crystallinity, then you heat it at the peak crystallization temperature. But it depends upon you that what sort of experiment you are doing. There are glass ceramics where you control the crystal size. In these material, the lower the temperature, the lower will be, the smaller will be the crystal size. The higher the temperature, the larger will be the crystal size. Lower the crystal size, favor highly dense materials. Larger the crystal size, favor less dense materials, because there occur many voids and gaps when the crystal size are large. They don't fit into the gaps and pores are left there, voids are left there. But it depends upon the material, what sort of material do you need. Sometimes larger grains give excellent properties because of the less number of grain boundaries. If grain boundary is affecting a specific property. Once you have known the calcination temperature, calcine the material in a furnace in the desired environment. If the material is highly reactive, people usually cover it with something. The temperature is gone properly. The heating rate must be given. The soaking time must be given. What happens in a furnace? In a furnace, you start from room temperature, take it to the desired temperature, for example, like this. Then you keep it like this. For example, this is the peak temperature. This is, for example, 5 degrees Celsius per minute. 10 degrees Celsius per minute, 1 degree Celsius per minute, depending upon the material, which sort of material you are using and how much sensitive it is to the heating or cooling rate. Once you have taken to the peak temperature, for example 1000, here you keep it for 1 hour, 5 hours, 10 hours, this is your choice. How much you want to equilibrate the desired phase, then you cool it quickly. Obviously, stresses will be arrested. You will freeze the material at particular state. You can very slowly cool it. Again, this is your choice and depends upon the material. Some people cool material at 3 degrees Celsius per minute, but still crack appear in it. This means thermal expansion mismatch inside the material is there. So people cool some material very slowly. And as I have told you in some of the lectures on metallic glasses or soft magnetic materials, they are cooled at very high speeds to suppress crystallization, and you make an amorphous metallic glass at the end, and then you crystallize it at your choice and undergoes nano stage crystallization. Once you have calcined the material, you have formed the desired phase. Do XRD of the material, check the phase purity. If it has formed, well, you have succeeded up to this step. If it has not formed, then some material don't form various phases or the desired phases readily. Some materials readily form the desired phase. So people again and again do calcination sometimes. Sometimes one calcination treatment is enough to make the phase. Now, when you have calcined the material, what happened? That slight agglomeration of the powder may occur because the chemical reaction has taken place, right? In order to make pellets is the required geometry for measurements of properties. For example, you are using a material as an insulator in transformer cores, right? You are using a material as a capacitor, a resonator, right? Resonators, the shape should be different, other will be different, but commonly at lab scale, people make pellets. So, before making pellets, you should re-sieve the powder to dissociate agglomerates, if any, and after sieving, store it in a bottle. Again, where to store it? It depends on the properties of the material. If the material is hygroscopic, if the material has some other contamination or something worries, then you have to do the same arrangement for that. Whether it should be stored in a desiccator or ordinary cupboard. But when you make the material, you take the calcined powder into a dye like this. Dye has a plunger here, and then you pour powder inside it. There is a plunger on the top. You press it with the hydraulic presses. There are different forms of presses: isostatic pressing, manual pressing, automatic pressing. So there are different sorts of presses people use around the world. So you press the material after keeping the pressure, for example, 100 megapascal. Again, the pressure is important because it gives the final shape of the pellet. If you overpress a material and when you remove the press, then it may crack. There are many different things. Some materials don't just press properly, and for that people make various additives, organic materials, to make them pressable. And when they are pressed into a proper shape, for example, this is for example the shape of the material you made, then this is called the green pellet or ace pressed pellet. Ace pressed pellet or a green pellet. You make, for example, I usually make 3 or 5 pellets like this. The die should be of a specific diameter, so this will be the diameter of the pellet. The thickness again is under your control. How much thickness do you want? Put more powder to make thicker pellets, put less powder to make thinner pellets, right? Once you have done it, then you take it to sintering. And the sintering temperature is again somehow it is above the crystallization temperature but will below the melting temperature, right? It is above the crystallization temperature, or you can say the calcination temperature may be well above the calcination temperature but well below the melting temperature, because you don't want to melt the material, and secondly you want to densify the material. So no phase formation is expected during sintering. The sintering process is that you have cardinite grains formed, and during the sintering these grains grow while making and filling the spaces among different grains. They densify, the voids and gaps are eliminated, and I have told you that if you have having pores or voids inside material means that you are marrying the property of air instead of the material. The minimum the pores, the minimum will be deterioration in the properties, right? So, and I have given you an example that if you have a conducting wire which is 100 miles long, but there is a small piece of 1 millimeter which is non-conducting, your conductor will not work, right? The same thing is here, that you are making a material which has, for example, 5000 is the value of the dielectric constant, right? But you have 50% of the material is voids and pores. So the dielectric constant of air is 1. So the properties you are expecting to be 5000 will be 2500, because you are measuring the property of the pore. That is why for electrical application people prefer to densify the material. The optimum density can be well above 95, but usually above 95 is considered sufficient. 95 means 95%. 95% means, how to calculate it? Just take the latest parameter of a unit cell and multiply them together, the height, the different dimensions of the unit cell and their mutual multiplication. For example, if the unit cell is cubic, then A into 3 is the volume of the pellet, and weight, how much atoms are coming in that unit cell. So their weight divided by the volume will give you the density of the unit cell, and that will be called the theoretical density. And when you take this pellet to the density meter, you dip it in water and the volume replaced. The Archimedes principle is usually used to determine the experimental density of a pellet. Experimental density divided by the theoretical density into 100 is the percent density, and the 95 which I mentioned is that percentage of density. Once you have done it, then again you need to machine the pellet. You are making a toroidal core, for example, so you need a hole in the middle of the pellet. You need to measure, for example, the dielectric constant, so it should be electrodic. Put electrodes on both the smooth surfaces, polish the surface so that it is clean, then put gold paste, silver paste, palladium paste. People make various mixtures to make the electrodes on the two surfaces of the pellet, and then they connect it and then they measure the properties. So this is for the mixed oxide route ceramics preparation, and these were the preliminary introduction that how people make these materials experimentally. And you know, this is a very easy thing but tricky as well. Some people make excellent material although they may not be academically that sound. Some people are academically excellent but they may not be producing excellent material. This means that in addition to knowledge, ceramics preparation is a skill as well. And if we look into the history of ceramics, it has developed through skill, not through knowledge. But now we have learned how to measure the properties properly and then make the engineer the materials at atomic scale and different levels. So knowledge has become more important, but skill is equally important. When knowledge plus skill come together, you take the product to commercialization. And that is why people develop economically because of their knowledge. So knowledge is combined with technicality, then the product goes to industry or commercialization. If the skill is missing or the knowledge is missing, you can't take a product to industry or society. Thank you very much. Any question?
Thank you.
Just
This the oxygen is adjusted automatically if let's say we need 19 times of oxygen, as in the formula it was 18 times. Let's say we need 19 times. Then what should be the procedure?
You don't need 19 times because when we studied in the material courses that charge neutrality is must. So FgO, Mg is plus 2, Al2O3, look at it, O3 minus 6, Al2 should produce plus 6, right? So this means Al is plus 3, Al is plus 3, Mg2, so it is plus 4, Al4 means plus 12, right? Al4 is plus 12,
3 into 4 plus 12.
plus 12, silica, SiO2, Si5, so 5 times 4, 20, so how much it? 16 plus 20, 36, 18 into 2, 36.
Yes.
So the negative and the positive must be matching, otherwise the compound will not be stable. If there is a deficiency of a cation, it will react with the immediate contact materials to neutralize that cation. And if it is deficient in oxygen, it will pull an oxygen from the air, from the environment to compensate or to fill that deficiency. So unbalanced charges cannot be stable. That is why the equation must be like that. Some people are now making materials in reducing or oxidizing environments to intentionally induce deficiencies. For example, for anion conduction, there must be a gap inside the material so that anion can travel and they can take that current. So people are making materials which are not neutral. They are inducing deficiencies, and this is commonly solid solutions of various materials are made, but in solid solution neutrality is equally important. You will have to balance the neutrality. If you are substituting something for magnesium then there are two conditions. That number one, it shouldn't disrupt the charge balance. It must produce a neutral compound. Secondly, the size of the cation you are substituting for magnesium must be within 15% ionic radii of the two must be within 15%, otherwise it will then form another phase. It will not be that phase. So the basic crystal structure, if you follow these conditions, the charge neutrality and the radii matching is followed, then you will make a compound which will have the same crystal structure. But if the cation is slightly larger or it is slightly smaller, right, this will affect the lattice parameter accordingly. Because you are measuring lattice parameter in terms of angstroms, and if the size is, for example, 1.4 and you are replacing it with 1.45, then that many angstrom proportional to that difference will occur in the lattice parameter of that material, and they are easily determined by X-ray diffraction. So mostly we look for neutral materials, but for inducing properties people do a lot of experiments with in reducing and oxidizing environments to induce vacancies and different things there. The amount also matters, that how much amount of the material you are substituting. If, for example, this is Mg2 minus X, and for example some other sodium or some calcium or something X is added, and it is forming the same phase, for example up to X equal to 0.5, and after that it shows a multiphasic material. This means that you have crossed the solid solubility limit of calcium or sodium in that